Hello everyone, welcome to my channel. This is Karuna, teaching the course Computer Architecture and Organization. Fifth unit, Memory Systems, contains the following topics, out of which we are concentrating on basic memory circuits in this video. Introduction. Memory is used to store data as well as programs. Before going to develop memory chip, designer of the memory has to keep all these requirements in the mind. Those are fast memory, large memory, and it should be inexpensive. But it is impossible to meet all these requirements simultaneously because increased speed and size are achieved at increased cost. Okay, so to solve this problem, it is required to develop clever structures of the memory to improve the speed as well as size by keeping the cost reasonable. There are several techniques to improve the size and speed of the memory. The speed of the memory can be increased with the help of cache memory, and the size also can be with virtual memory. Let us see the basic concepts of the memory. Memory size can be determined with the help of address lines, or we can say the maximum size of the memory that can be used in any computer is determined by the addressing scheme. Suppose two address lines are there. Okay, so 2 power 2 equal to 4 memory locations. Okay, so this is the power of 2. So 2 address lines can address 4 memory locations. Okay, for example, this is one location, this is another location, and so on. There are 4 memory locations: 0, 0, 0, 1, 1, 0, 1, 1. We will get 4 combinations from 2 bits. Okay, 0, 0, 0, 1, 1, 0, 1, 1. 2 address lines are required to point the 4 memory locations because 2 power 2 equal to 4. Okay, 2 are the address lines and 4 are the memory locations. So if you want to select first location, you need to send 0, 1 bits on address lines. Okay, so 2 address lines are required to carry these 2 bits. If you want to select fourth memory location, then you have to send 1, 1 address bits on the address lines to memory. Then this memory location will select. Likewise, in this example, 16-bit computer that generates 16-bit addresses, which is capable of addressing up to 2 power 16 equal to 64K memory locations. Okay, similarly, if you take machine instructions, generate 32-bit addresses can utilize a memory that contains up to 2 power 32 equal to 4G memory locations. Most modern computers are byte addressable, means memory location stores 8 bits. 8 bits we can call it as 1 byte. Each memory location stores 1 byte. Okay, that's what here 64 KB. Can say 64 locations used to store 64 bytes. Okay, here 4 gigabyte. Okay, means byte in the sense each location stores 8 bits. If you take memory location size is 8 bits, then we can call it as byte addressable. Like that, memory sizes can be varied by varying the address lines. Let us see how the data transfer takes place between processor and memory through address bus, data bus, with the help of control lines, read write, memory function, complete control. Data transfer takes place between the memory and processor through the use of two processor registers. Those are MAR and MDR. For example, the size of MAR is K bits. That's what it can transmit K bits to the memory with the help of address bus. Okay, so MDR can store N bits. MDR register can store N bits. Assume like that. So that's what it can transfer N bits over the N data lines. Group of data lines, nothing but data bus. How many address lines here? To carry K bits, it requires K lines. Okay, so that's what the capacity of the address bus is, K bit. That's what we can say, K bit address bus. It can carry K bits. Okay, so if the address lines are K bits, how many combinations will get? 2 power K. Okay, so that's what here, up to 2 power K addressable locations. 2 power K memory locations can be addressed by the K bits, K address bits. So during a memory cycle, N bits of data are transferred between processor and memory. This transfer takes place over the processor bus, which has K address lines and data lines. The bus also includes the control lines. Those are read or write bar, memory function complete control signals, etc. These control signals are using for coordinating data transfers. Okay, so in this example, the directions are indicated for transmitting the data from memory to processor. That means read operation is performed by the processor. Okay, let us see how read operation is performed. Because of read operation, the direction of the data lines are towards processor. Means processor collects the data from the memory through data bus with the help of this address. Okay, let us see how read operation is performed. Processor reads the data from the memory by loading the address of the required memory location into the MAR register and set the read write bar line to 1. Okay, so here because of read operation, this control signal will be active high. Because R is active high signal, W bar is active low signal. If the signal is 1, it performs read operation. Otherwise, it performs write operation. Okay, so that's what we can say. Read signal is active high signal, write signal is active low signal. Okay, the memory responds by placing the data from the addressed location onto the data lines. Okay, so suppose processor sends all K bits are zeros. Okay, so first 0th memory location will be selected. At that address, whatever the data is present, that will be loaded onto the n bit data bus. Okay, and confirms this action by asserting the memory function complete control signal. Upon receipt of the MFC signal, the processor loads the data on the data lines into the MDR register. Memory function complete control, when it will be activated, whenever the data is placed on the data bus by the memory, then MFC control signal will be activated. After receiving the MFC control signal, processor collects the data from the data bus to its MDR register. Likewise, processor performs the read operation from the memory with the help of this MAR register and MDR register, as well as address bus, data bus and control bus. So coming to the write operation, the processor writes the data into a memory location by loading the address of this location into MAR, loading the data into MDR and setting the read-write signal line to 0. Okay, in this case, read operation is performed. That's what the direction of this data is like this. To perform block transfer operation, then only it will send one address to identify its first location. This memory access may be synchronized using a clock. Let us see some important points. Memory access time. It is the time that elapses between the initiation of an operation and the completion of that operation. For example, time between read and the memory function complete signals. Okay, so coming to the memory cycle time, which is the minimum time delay required between the initiation of two successive memory operations. For example, time between two successive read operations. Okay, so a memory unit is called random access memory if any location can be accessed for a read or write operation in some fixed amount of time that is independent of the location's address. If we reduce the memory access time, then speed of the execution may be increased, automatically system performance may be improved. So there is one way to reduce the memory access time is to use a cache memory. Okay, or we can say with the help of cache memory, memory access time can be reduced. Let us see one internal organization of the memory chips. Memory contains locations. Here each memory location stores any number of bits. So in this diagram, memory location contains 8 bits. To store 8 bits, 8 memory cells are required. Okay. Each memory cell is capable of storing 1 bit of information. These memory cells are connected to a common line known as word line. Okay, these cells are organized in the form of array. Okay, so rows and columns. Okay, all cells of word line is connected to the address decoder. Next, data input output lines of the memory chips are connected to the sense or write circuits. Each memory location stores 8 bits. Those are B0 to B7. Each location is connected to one word line. That is, first line is connected to W0. Okay. Likewise, here how many rows are present? 16 rows are present. Okay, that means 16 memory locations are present in this structure. That means this memory can be used to store 16 words. To address these 16 memory locations, 4 address lines are required. So that's what A0 to A3. Okay, so these 4 address lines are connected as input lines to the address decoder. Okay, now the decoder will select the required memory location, that means required data. Okay, so suppose if processor wants to get the data from first location, then it will send all 4 zeros on address bus. Okay, group of address lines, nothing but address bus. Okay, so if processor sends all ones, then W15 line will be activated. The cells which are connected to that line will be selected. At that particular bits will be transferred through the data lines B0 to B7. These are the 8 data lines are used to transfer 8 bits of data. Okay, so here these are the control signals. These control signals are coming from the control unit. So based on this control information, read or write operation will be performed by the processor. Okay, before that this chip will be selected with the help of this chip select signal. Each cell is made up of semiconductor material. So semiconductor memories are available in a wide range of speeds, range from 100 nanoseconds to less than 10 nanoseconds. Introduced in 1960s, they were much more expensive than the magnetic core memories. Because of rapid advances in VLSI technology, the cost of semiconductor memories has dropped dramatically. As a result, now they are used in implementing memories. So this is the word line. All cells of row are connected to a common line known as word line. Okay, so this word line is driven by the address decoder. Let us see the read operation. During read operation, the sense or write circuit read the information stored in the cells selected by a word line and transmitted this information to the output data lines. Okay, so these are the output data lines. Okay, so this memory transfers the data to the processor through these output lines. Data bus having bidirectional lines. Okay, this line is for receiving the data, this line is for transmitting the data. Okay, so likewise in and out transfers takes place through this data bus. So here address is sent by the processor. So that's what we can say, these lines are unidirectional lines. Data lines are bidirectional lines, in and out lines. During a write operation, these sense or write circuits receive input information and store it in the required cells of the selected word. Likewise, read and write operations are performed with the help of control signal and address lines. Okay, this is another internal structure of, we are taking 1K into one memory chip. Means if you mention 1 is nothing but one cell. If you mention 8, okay, that is nothing but 8 cells. Let us take one example, 1K. 1K means 2 power 10 equal to 1024. Okay, 1K locations. That location may store 1 bit or 8 bit or 16 bit or 32 bit. Okay, so but here 1K means 1K locations. Okay, that location may contain 1 cell to store 1 bit or 8 cells to store 8 bits, 16 cells to store 16 bits, or that location contains 32 cells to store 32 bits. Okay, likewise the cells can be organized. Okay, now let us see how the cells can be arranged in this way. Okay, so 1K means 2 power 10 means 10 address lines are required to identify or to point 1K locations. That's what here 10 address lines are used to carry 10 bits. Suppose 1K memory cells can also be organized like this. Okay, 32 into 32 means 32 memory locations. Each location stores 32-bit data. Means 32 rows, 32 columns. So that's what, to get 32 combinations, we need 5 address lines. That's what, address lines divided into 2 groups of 5 bits each to form the row and column addresses for cell array. 2 power 5 equal to 32. These 5 address lines select a row of 32 cells, all of which are accessed in parallel according to the column address only. Column address, only one of these cells is connected to the external data line by the output multiplexer and input demultiplexer. Out of 32 bits, we can select any one bit. So that's what, one line is used to carry one bit. To select 32 columns, okay, 5 address lines are used. Here, to select 32 rows, 5 address lines are used. With the help of 5-bit decoder, any one of the memory location out of 32 memory locations can be selected. And also, we can select 1 bit of data out of 32 bits with the help of these 5-bit column addresses. Columns are connected to the data bits. Okay, for example, if processor sends all zeros, okay, then first column will be selected. If processor sends all ones, then last column will be selected. Here, if processor sends all zeros on the address lines, then first row will be selected. That means all memory cells connected to that line will be selected. After selecting one row, in that row we can select any one of the column cell, okay, to transmit 1 bit of data. Likewise, with the help of the sense and write circuitry and read or write control signal, processor can perform read or write operation with the memory. So these two figures are commercially available memory chips. Okay, this one and this one are commercially available chips. Likewise, memory cells or memory chips can be organized to perform read and write operation. Thank you. We will meet in next video.